Theoretical probability models provide the structure for how events occur, but until we identify precise numbers anchoring that structure to data, the model remains a mathematical abstraction that cannot be applied to the real world. In applied statistics, we rarely have the luxury of knowing the true underlying numbers. Instead, we have raw observations. We have to work backward from that data to learn the rules. We refer to this unknown target as theta. It represents a fixed numerical feature of reality that is built into the model, but is completely hidden from us. To bridge the gap between data and theory, we rely on an estimator. This is a mathematical rule or a specific formula that we apply to our sample data in order to make a calculated guess about theta. As seen here, we must strictly separate the true parameter, theta, from the specific numerical output generated by our formula, written as theta hat. Extracting these parameters requires choosing between two dominant, philosophically opposed frameworks: maximum likelihood estimation and Bayesian updating. Choosing between a frequentist point estimate and a Bayesian distribution dictates whether we treat our objective as a single fixed value or a shifting landscape of probability. The same unknown parameter can have multiple candidate formulas used to estimate it. To choose the best one, statisticians use a strict mathematical grading system. The first metric is bias. An estimator is unbiased if its expected value perfectly aligns with the true parameter across repeated samples. It means the formula is correct on average. The second metric is variance. This measures how wildly the estimator's guesses fluctuate from one sample to the next. We visualize this on a standard bullseye, each hit representing a single estimate. An unbiased but highly variable estimator scatters widely around the center. Conversely, a highly precise estimator with systemic bias lands entirely in the wrong quadrant. Mean squared error acts as a balancing scale, combining variance and squared bias into a single metric. This dynamic creates the bias-variance trade-off. To achieve the lowest possible total error, it is sometimes mathematically superior to accept a slightly biased assumption if it drastically reduces chaotic variance. The foundational approach to extracting parameters relies on the frequentist perspective. Here, theta is treated as a fixed absolute constant, and we estimate it using nothing but the observed data. We do this using the likelihood function. This measures how probable our exact observed data is at different candidate values of theta. Note a critical constraint. The likelihood function is not a probability distribution over theta. It evaluates plausibility, but the area under its curve does not integrate to 1. This chart shows how likelihood operates for a Bernoulli dataset of ones and zeros. The likelihood function arches over the space, mapping the plausibility of every potential parameter value. Maximum likelihood estimation asks, which specific parameter value makes the data most probable? To find it mechanically, we convert to log likelihood to turn multiplication into simple addition. We differentiate and set the derivative to 0. The tangent line slides to the absolute apex, flattening to a slope of 0. Dropping a vertical line gives our exact maximum likelihood estimate, k over n. MLE serves as the primary optimization principle for logistic regression and neural network training because, as data volume grows, its estimates are mathematically consistent and asymptotically efficient. But it has a strict limitation. MLE outputs a single point estimate. It gives you the best guess, but remains mathematically silent on how confident you should be in that specific number. The Bayesian framework takes a different path. Instead of treating the unknown parameter as a fixed point, Bayesians treat it as a random variable with its own probability distribution. In this split view, we contrast the static frequentist point against the core Bayesian equation. A Bayesian updates their prior belief by multiplying it by the likelihood of the new data, creating a posterior distribution. Historically, achieving this posterior required finding a normalizing constant. That meant solving intractable calculus and running complex integration over the entire parameter space. To bypass that integration, statisticians rely on a mathematical shortcut known as conjugate priors. Conjugacy occurs when the prior distribution and the resulting posterior distribution belong to the exact same mathematical family. When this rule applies, updating your belief requires only basic arithmetic. Observe a beta binomial conjugate pair. Our prior belief is a wide beta curve with parameters alpha 3 and beta 7. we observe 15 conversions and 25 failures. Because they are conjugate, we skip calculus and just add successes to alpha and failures to beta. The curve instantly morphs into a narrow beta 1832 posterior. This full distribution inherently tempers the new data with our original prior knowledge, whereas an MLE point estimate would have just reported the raw 15/40 ratio. The Bayesian posterior yields a complete distribution. By doing so, it inherently quantifies our exact level of uncertainty, turning a static guess into a dynamic, mathematically rigorous belief system. Because it uses simple arithmetic, conjugate Bayesian updating is highly efficient for continuous streaming data. We handle this through sequential updating. The logic is cyclical. The posterior distribution you calculate after today's data directly becomes your prior distribution for tomorrow. This chart visualizes what happens when a highly inaccurate prior belief collides with a massive influx of continuous data. On the left, our prior curve is positioned completely incorrectly. On the right, the static dot marks the true, data-driven MLE estimate. As the simulation begins, new observations stream in, and the data count rapidly accumulates. This rapid influx triggers prior washout. The sheer mathematical weight of the likelihood overtakes the original prior parameters and drags the curve toward the objective data. As the data volume explodes, the variance of the distribution collapses inward. The uncertainty is stripped away. Ultimately, the peak of the Bayesian posterior snaps exactly onto the frequentist MLE point estimate. As the sample size approaches infinity, the prior is entirely washed out, and the Bayesian and frequentist estimates perfectly agree. In practice, statisticians deploy maximum likelihood estimation for fast, computationally cheap point estimates, especially when data is incredibly abundant. They rely on Bayesian conjugate priors when data is scarce, expensive, or when structural uncertainty requires careful quantification. In a world of infinite data, theoretical philosophy eventually yields to mathematical certainty. But when data is scarce, choosing the correct analytical framework is the only reliable way to map the unknown.